Hello everyone, Assalamu alaikum wa rahmatullahi wa barakatuh. I'm speaking to you from the MUH. I'm Ahmed Waqqas Al-Awlaqi, a member of the brilliant group consisting of Ramadan, my dear friends Ramadan, Mohammed Taneji and Ali Al-Mahrizi. So today we'll be presenting our project for AI 1030 called the Volt Runner. In this project we designed a small programming language and interpreter to control a robot inside the grid world. So a bit of an overview on our project. Our task was to design a mini programming language for a robot called the Runner. The Runner lives in a Volt-like 2D grid world with walls, a key, a door and an exit. So the robot's main objective is simple. It must collect the key, open the door and escape. Or if it also simply finds the exit directly, it can simply do so, escape immediately. We worked under strict constraints that were given. The robot can only sense its immediate surroundings. The language was limited to 20 tokens or less, and only one simple memory flag was allowed. Our challenge was to create a functional, compact language that could solve different escape scenarios under these limits. So in regard to our design goals, our design was shaped by four main goals. First, simplicity. The language should be easy for beginners to read, write, using just a small set of keywords. We were, of course, inspired by other simple programming language, so applying that to our language was rather important. Second, functionality. Even with few tokens, the language had to cover all the essential actions, which is moving, turning, picking the key, opening the door, and most importantly, of course, escaping. Third is clarity. Every token in the language has a direct and obvious meaning, so programs are deterministic and easy to reason about and also understand. Finally, constraint-driven design. Every choice we made was shaped by the assignment rules: fewer than 20 tokens, one flag for memory, and a boundary in the grid world. So, with our language features a bit technically, our language is built around 5 main features. First, the actions. Move means the robot goes one step forward into the tile in front of it. Left means the robot rotates 90 degrees to the left, changing its facing directions, but not its position. Right means the robot rotates 90 degrees to the right. Pick means the robot picks up the key if it's standing on it. Open means the robot opens up the door if it's currently in front of it and holding the key. And the second part, in regards to sensors and conditions, front checks if the tile in front of the robot is clear. Key checks if the robot is standing on a key tile. Door checks if the robot is standing on the door. Exit checks if the robot is standing at the exit. And that would be it in terms of conditions. Now to the control flow. If statements allow the robot to take actions only when a condition is true, with the else blocks for the alternative option. We use the combination of an infinite loop with a break statement. This design keeps the language simple while still letting programs terminate. Because the Volt world is always bounded, the robot is guaranteed to eventually escape. So this approach is safe, effective, and rather, how can I say it, accurate. So in regard to memory, as was mentioned in the constraints, the robot has one Boolean flag. We can set the flag to remember events such as collecting the key and clear it when the event is no longer relevant. So finally, and I want to be delving deep into this, regarding the macros, these are reusable shortcuts made from core tokens, like sweep, shift, and shift right. They make program shorter and easier. Now my friend Mohammed will go through all of these details in the next slide. Thank you very much.
Okay. So here we are showing how the sweep macro actually expands into detailed instructions. So I'll explain what the code does. First, we prioritize the exit. So if we find the exit, we just escape. Then key, if we find the key, we pick it, we set a flag. So this means I am holding the key. Then if I am holding the key and I am in the tile where there is a door, I will just open it since I have the key. I will clear the flag and then break, just escape through the door. Otherwise, I will just keep moving forward. So the sweep function is really powerful. It helps us to cover an entire column or entire row with just one function. Regarding the shift right and shift left is simply right, so facing 90 degrees to the right, move one tile and then face right 90 degrees to the other side. And I will explain why it's powerful and helpful, the shift left and the shift right. It will be really helpful for implementing the zigzag traversal algorithm for program or for the task number 2. Regarding the grammar section, our grammar is intentionally simple. A program is just a sequence of commands written one after the another. So each command can be an action like move or pick, a condition block, a loop block, macro, or a break statement inside a loop. Regarding the semantics means what the commands actually do. For example, move always steps, you can say forward exactly for one tile only. The left means always turns the robot 90 degrees to the left, and the same goes for the right function, which is moving 90 degrees, not moving, so I mean facing 90 degrees to the right. And then the if checks a condition and only runs its block if true. Regarding the loop, it always repeat because we have infinite loop until a break is reached. So here the first task, which is the twisting corridor, and it's mentioned that the robot can start anywhere and in any direction inside the corridor. There is a key, a door, and an exit. So I will just use a simple map to explain how our code is working. This is arrows, I will just go through it. So the main things that we are prioritizing in order, which is the exit. If we find it, we directly escape. The key, if we find it, we simply pick it. Similar to sweep, but it's a bit different because there will be some rotations. If we find the door, we open it, we clear the flag, we escape the door. Otherwise, if the checking part is not, done, then we will execute this function, which is front, which means if the tile that's in front of me is clear, I will just move one step. So if our robot is here and facing this direction, we will see all these functions. Okay, there is no exit, there's no key, there's no whatever. We will move one step, we will move one step, we will move one step, we will move one step. Okay, now it's not clear. What we will do, we will turn left. Oh, there's a block. Then we will turn right, we will be in the same condition as we were before, and then turn right again to face this direction. Then we move one step. Also, for every step, we check what's called the exit key and the door. One step until we reach here, or we'll face left again. It's not clear, right, and then we move. So this is simply our code for this task. And the total tokens is 39. Regarding the second task, which is a rectangular room with no obstacles inside, and here I will show you how powerful the sweep and the shift right, shift left function is. The task is that the robot starts at the bottom left corner facing north. The room contains a key, a door, and an exit. So in this code, we used only 6 tokens, which is sweep, shift left, shift right. But if we expand them, it will be actually more than 6, because the macro itself holds a lot of tokens. So I will show you how we implemented the zigzag traversal. So we've mentioned that sweep will go through the entire column. Yeah, it will keep moving forward. And before moving forward, it will always check if there is a key, if there is a door, exit. If not, it will just keep moving forward. And then once we reach this point, since there is no obstacles, we can implement the zigzag traversal easily. So it will shift right. Shift right means face right, 90 degree, move one step, and then face right again. So we are facing downside. And then sweep. Then shift left, facing left, taking one step, and facing left again. Then sweep. And here we will take the key. Again, shift right, sweep, shift left, sweep. We reach the door. So as here mentioned, if I hold the key, I will open the door, and then I will just escape through the door. This is for task number 2. Now I will leave you with Ramadan Sado for the next slides.
We've separated interpreter to 4 main parts: tokenizer, parser, and executor. Each part does its own role. For example, tokenizer just reads main.rbc file and splits everything into uppercase tokens. Also, then we use a parser in order to parse all of these tokens and build upon our program. And on which parser our it uses also structures from executor. Executor basically performs all the operations that the robot does in our program, which were programmatically written in our code, in .rbc code. And Robot API provides sufficient API in order to manipulate the robots. For example, all the API that use it in a robot.api file is concretely used in the executor.py. So there's like some sort of blocks, for example, blocks of code in the robot.api, which are beautifully constructed in the executor.py. And in this case, we implemented 3 test cases, which can be seen in our report. Let me just show how interpreter works in the real world. Yep. Wait a second, I just need to. Yep. As you can see, everything the user needs to do is just copy the contents of .rbc file into main.rbc file, because our interpreter reads specifically only main.rbc files. Also, as you can see, in the beginning of our program, we can specifically show the map that we need to use. It adds scalability to our user because he can add his own maps and provide his own test cases. Yeah, as you can see, everything we need to do is just run interpret.py in our case.
At the end of this presentation, we're gonna reflect on what we learned. First of all, we have trade-offs. There were trade-offs in every design decision. Staying under 20 tokens meant we had to keep the core minimal, and allowing one flag limited what we could express, but it was still powerful enough for the required tasks. Using infinite loops with breaks was not elegant, but it worked in our bounded worlds. The main lessons we learned is that language design under constraints is all about prioritization. Simplicity and clarity make programs more reliable, even if they lack advanced features. Also, macros helped us keep programs readable without breaking the rules. Overall, this project showed us that constraints are not just limitations, they can also guide us to create more focused and elegant solutions. Thank you for listening.